George Hermens is here with us today for his 7-minute high-speed lecture about a recently reached milestone in the coatings flagship, the University of Groningen and AkzoNobel made a polymer coating. You just heard something about it in the animation. From the woody parts of plants using bubbles of oxygen and light to trigger a key reaction in a water-based solution. This sounds really great and promising, but we also need to learn a bit more on it. And therefore we ask you.
I will tell you everything.
I wish you all the luck. Success.
Thank you very much. All right, good afternoon everyone, and welcome to my high-speed lecture, which is about the work that we, the University of Groningen, have been doing together with AkzoNobel about bio-based coatings. To start, coatings are omnipresent in daily life, indispensable in construction and used everywhere around us to enhance the durability of numerous products. Whether it be your car that you drive to work in the morning, your smartphone that you use daily, or your wood that you have in and outside of your house, you can find the coatings everywhere. Diving a little bit more into depth of what coatings are. Coatings are cross-linked networks of polymer chains covalently bonded together. And these polymer chains are built up of smaller monomers. And one of the most well-known monomers used in coating industry are these acrylates, which are being produced on a multi-million ton scale per year, all coming from the petrochemical industry. However, fossil fuels are of course a finite source. And with the ongoing trend of humanity consuming more and more of these fossil fuels, it means that we will run out of fossil fuels within a few hundred years. Concurrently, transformation of fossil fuels into molecules of higher application also results in the production and emission of CO2 and other greenhouse gases. So it is evident that we need sustainable alternatives in tomorrow's chemistry and materials. So I sketch the current process. You start from the oil, you go to the monomers, and then you polymerize this into the coatings. However, we want to have a sustainable competing process that not only should start from biomass, but should also overcome 3 important challenges. The first one of which is a sustainable synthesis. For example, by implementing oxygen from the air and light as viable reactants for the synthesis. We, of course, also want to have a scalable synthesis, since we need to compete with the industrial acrylate production process. And our acrylate alternative that we want to produce should, of course, have similar properties as the monomer we're trying to find a replacement for, the acrylates. We propose that this butynolide structure is a viable, sustainable alternative to acrylates. As you can see, it contains the same unsaturated ester that you find back in the acrylates that is required for the polymerization process. Furthermore, it contains an R handle that can be introduced in a similar way it can be introduced in acrylates. However, to become a viable alternative, it needs to overcome the 3 important challenges. The first one, green synthesis. Starting from the platform chemical furfural, which is actually being derived from waste biomass material. It can react with oxygen and with light in the presence of a photocatalyst to generate fully selectively our hydroxybutynolide non-substituted monomer. It can then react with any alcohol, albeit for example bioethanol, to generate our alkoxybutynolides selectively. All in all, we have a very green synthesis since we only need oxygen, visible light, a catalyst and an alcohol to go from our platform chemical towards our desired monomer. The scalability is also a problem that we have tackled. Back in the lab at the University of Groningen, we designed and developed a continuous flow setup by taking a TL bulb, wrapping a very thin tubing around the TL bulb and having a flow of oxygen coming from one side and a flow of our solution containing our catalyst and our substrate coming from the other side. Upon the irradiation, we generate continuously our non-substituted monomer. Although this is of course still produced on rather small amounts as compared to the industrial processes, this is already a step towards potential scale-up. So at least this this scalable synthesis has also been achieved. And at last, we're also interested in whether it has similar properties. To have similar properties, we of course need to react it in a similar way. So what we did, we took a reaction mixture of our bio-based butylenolide together with a crosslinker that you need for your coating, and we add a photoinitiator. We apply this on the glass plate, and we irradiate it for 5 minutes with UV light. And then we obtain our bio-based coatings on glass. So in that sense, also similar properties have been achieved, as they can react in a similar way. We can also react our acrylates. In the end, we produced bio-based coatings on glass, transparent hard coatings with excellent resistances against water and solvent, so they don't scratch off upon in the rain, for example. And the properties in terms of hardness are very similar to existing acrylate-based coatings, making it a very viable, sustainable alternative. But that's not everything. Above all, we are able to change the size of the butylenolide. And by changing the size of the butylenolide, we can change the properties of the coating. We can, for example, make it more hydrophobic, in which we are able to coat even on plastic surfaces. So glass and plastic are no problem whatsoever for us to coat our coatings on. To conclude, we start from a platform chemical and developed a sustainable synthesis route, including oxygen from the air and light as viable reactants to generate our alkoxybutylenolides as viable acrylate alternatives. We polymerize this into bio-based coatings. And the outlook of the project lies actually in the upscaling. We are currently in the process of scaling this up even further. We are currently in the process of developing new reactors that can produce a few kilograms per day. Having then lots of material in hand, we can of course look for real applications, for example to coat on cars, which we can do at the AkzoNobel site. And at this slide, I would like to end and say that we are very proud of all the attention that we got after publishing our work last December in Science Advances. We are very eager to continue our research and to aim for a more sustainable future. Thank you very much.